Okay, while you're getting ready, just a quick review of yesterday. Yesterday we went over the questions for the structure of the atom, okay, reviewed what things were important within the history of the atom. So John Dalton and his 4 points of his atomic theory, and we went over like Rutherford's gold foil experiment, Thomson's discovery of the electron, okay, and then of course de Broglie's sort of idea of the electron cloud model for the atom, which is what we currently accept. Okay, those are all things that you should review. By the way, did I mention yesterday that you don't have a quiz tomorrow? Yeah. Okay, so just to clarify, you do not have a quiz tomorrow. Okay, and then we went into ionic compounds. We started talking a little bit about how they work. Okay, they're obviously a metal and a non-metal that are joined together. The joining process for an ionic compound involves the trading of electrons, okay, or the donation and accepting of electrons. Metals typically give the electrons, right? They donate the electrons. The non-metals are typically the ones who accept them. And what that does is it creates a weak bond between a metal and a non-metal that can be easily broken because they now have their outer shell of electrons full. And that's what we ended off with yesterday, was kind of showing how that worked for a simple compound like sodium chloride. Okay, so sodium, as we said, has 11 electrons. So there's 2 in the first shell, there's 8 in the second shell, and then there's 1 in the last shell. And the last shell can hold 8. So it's very difficult for sodium to fill that outer shell, but it's very easy for it to give up the single electron and then have its next shell down, which is full, be its outer shell. That's typically what metals do. Their outer shells are typically less than half full, so it's easier for them to give away electrons than to try to catch enough to fill it up. Chlorine, on the other hand, is the perfect match. It has 17 electrons, so first shell full, second shell full, and third shell 1 short of full. Okay, so it's a perfect match for chlorine because it needs 1 electron to get its outer shell full, which is much easier than trying to find a home for 7 electrons. So those two go together, they trade the electrons. Once they trade electrons though, if they split up, they stay the way they were in the compound. So that means chlorine has 1 extra electron and sodium is 1 short. Will they be electrically neutral now? So now sodium, okay, which normally has 11 protons and 11 electrons, now only has 10 electrons, and it still has 11 protons. Is it now charged? What do you think? If it's got 1 more proton than electrons, would it have a charge? And that charge would be positive 1. Okay, because it's down 1 electron. So now it has a charge of positive 1. And this is where, if you recall, I asked you this yesterday, where you get the drop and swap from. Sodium is going to be 1 short. It has a positive 1 charge. Chlorine has picked up an extra electron, so it has a charge of negative 1. Then you do your drop and swap and you figure out what numbers should go in there. If we had something like this, calcium with bromine, okay, calcium has a 2+ charge. It gives up 2 electrons. Bromine can only take 1. So when we drop and swap, we find out that if those 2 things are going to go together, there have to be 2 bromine atoms in order to make it work. Okay. Calcium's got to give up 2 electrons, so we need 2 bromines there to take the 2 on. Everybody following that explanation? All right, so what we want to start off today with is naming of the compound. So actually writing out their names in words. So the rules are, okay, and this should be familiar from Science 9, is that we write the name of the non-metal first, and then we write the name of the metal first, then we write the name of the non-metal, but we change the ending to I. Simple as that, okay? Nothing terribly difficult, right? So if I gave you this compound here, what would you call that?
Lithium oxide.
That would be lithium oxide, right? Even if there are little subscript numbers in a compound, if it's ionic, we do not acknowledge them. Okay? We don't put prefixes like di and tri or anything like that into an ionic compound, because this is the only way lithium and oxygen can go together. And the reason for that is lithium only has one electron to give away, but oxygen needs two. Okay, so when we drop and swap, we would need two lithiums in order to fill the need of the oxygen. Okay, so that's where we get that from. Okay, everybody all right with that? Okay, so things to remember. Make sure to name both. The metal's name is not changed. You write it exactly as it appears on your periodic table. The non-metal is changed to "ide," and that's all you do. Okay, there's nothing else to it other than that. Okay. Now, another thing here, this is a bad habit that everybody has. Okay, the names of chemical compounds are not proper names. Okay, it's not like, you know, John Smith. Okay, that's a proper name, so that would be capitalized. Sodium chloride is a chemical designation. It's not a name, okay? So you wouldn't capitalize it unless you were starting a sentence with it. Right, then of course you would, because those are the rules of English as I understand them. Okay, I don't teach English, but I understand you're supposed to start a sentence with a capital F. So these should not be capitalized. You're not going to get it marked wrong if you do, but know that the convention is they're not a proper name, so they shouldn't be capitalized. All right, I would like you guys to try the first four there. Okay, I'll give you a few minutes. Okay, write them down and then write down their names under or beside them, however you're going to arrange it. Okay, let's quickly go over this. Obviously, we've done the first one already. Okay, Na stands for sodium. Okay, so we go sodium. That's the name of the metal. Okay, and then this is chlorine, so we would call it chloride. Yeah. And there we go. That one's done. Number two, what does K stand for? Potassium. Yeah. Okay, and F? Fluoride. I always spell it wrong. I spell it flour. It should be F-L-U, right? It never looks right the other way. You ever had that feeling where you write a word, you know it's spelled wrong, but when you spell it right, it looks wrong? Okay, there's actually a word, there's actually a name for that. It's like some sort of psychological thing. Okay, HI, what would we call that stuff?
Would it be, well, H is hydrogen.
Mm-hmm.
Would the I be iodine?
Iodide, yeah. So hydrogen, iodide. Hey, is hydrogen a metal?
No.
What side of the periodic table is it on?
It's on the left.
Yeah, isn't that where all the metals are?
Yeah.
Hydrogen is a metal. It just happens to be a gas. Okay? Hydrogen is weird. Hydrogen can actually act both ways, but it is typically a metal. In fact, it is the most metallic substance there is. Okay? And I know that seems weird because it's a gas. Okay? But it very readily gives up its proton. Okay? Its electron. Very, very readily. It's happy to do it and have no outer shell. Okay? No outer shell is, well, as good as having a full outer shell. Okay? But it very readily gives up its electron. Okay? More readily than basically anything else. And that's why all acids have hydrogen acting as the metal. Okay? Because it very easily donates its electron. Okay? So hydrogen actually is a metal. Okay? But it can behave as a non-metal as well. Okay? It's very strange. It's just one of those things. Okay? That's, you know, if there's a rule, there's an exception to it. Hydrogen's the exception here. All right, and number four, what's calcium? What's calcium? Ca, that's what it is. Spoiler alert. Okay. Okay, and what's the other part of this? Bromide. Right. So it's bromine, but we would write it as bromide. Is that ringing the bell from last year?
Yeah.
Okay. I'll give you a few minutes on the rest of these, and then we'll go through them together here. Okay, so write them down and give them a try. So we just say aluminum. I'm fine. You spell it either way. I'm going to mark it right. Either one I interpret is correct. Okay. So it is aluminum because that's how we say it. Okay. And what's At? Astatide, right? Okay, aluminum astatide, astatine actually, but whoop, too many S's. Okay, what about number 6? What's CS? Cesium, yeah. Whoop, look at that, I put a capital on it. See how easy that is to do? Cesium. And what's S? Sulfur, and so we shorten that to sulfide. Okay? Sometimes it's tricky to decide where to cut off a non-metal if it doesn't end in "ide." It's easy. It's easy if it ends in "ide," but if it doesn't, sometimes a little trickier. For sulfur, you take off the and you put in the "ide" there. All right. For this one here, sodium, okay, is our metal. And what's O? Oxygen. Yeah. So oxide. Yeah. Not oxygenide, just oxide. Okay, we just replace it there. What does Ba stand for? Barium. Okay, yeah. And what's Se? Selenium, yeah. There's 2 ways you can write this one. Okay, I prefer the short one. Selenide. You can also write it selenamide. Either one is fine. Okay, whichever one rolls off the tongue better for you is totally fine with me. Okay, number 9. What does Ra stand for? Radium. Radium, yep. Telluride. Which I found out the other day is a city in Colorado. Yeah, it's not a Hyundai built SUV. It's also that apparently. Okay, but yeah. Sorry, I thought you had your hand up. Okay, number 10. Li stands for lithium, and F fluoride with the U first there. Okay. How many people are done to 14? Okay, I'll give you like another minute or 2 to finish up if your hand's not up, and then we'll go through those ones. So for number 11, Rb stands for rubidium. And S, sulfide. It's supposed to be an M. Sulfide. And look what I did again. See how easy that habit is to get into? Number 12, what does SR stand for? Strontium. Yeah, or strontium, whichever. It's another one of those ones that's written 2 ways. And I? Iodide. Number 13, calcium oxide. And 14? Magnesium selenide or magnesium selenamide. All right, not a prefix to be seen. All right, we don't use those in ionic compounds. We will use them extensively in molecular compounds, and we'll talk about that in a little while. Now, let me pose you this question. What would you call that stuff? Copper iodide. Okay. What would you call this stuff? Copper iodide. Is that a problem? Actually, it is. That's 2 very different things that have the same name. Okay. That could be a problem because one of those might be really good for you and the other could be acutely toxic. And if you say to somebody, hey, you know what, I discovered the health benefits of copper iodide, and they drink the wrong one and die, that's kind of on you. Okay? It's kind of a big deal. If these 2 things have different physical and chemical properties, which they certainly would, I'm just making up that whole part about one being good for you and one being toxic. Okay, I'm just using it as an example. Okay? But they would have different physical and chemical properties. They can't have the same name, right? You can't call two people by the same name unless you're mean. In one class about 12, 15 years ago, I had two Chase William Andersons. And those two people could not have been more different. Okay, but they had the same first, middle, and last name. It was really hard to sort out the grades and make sure I was getting the right one. Right? Actually, it wasn't that hard because they were very different, those two people. Okay, but they have the same name. That's kind of a problem. These two things would have the same name as well. This can happen with lots of ionic compounds that have what we call, or what we would call are multivalent metals. It means that they can give off different numbers of electrons. Sometimes they give off 2, sometimes they give off 3. In the case of copper, sometimes 1, sometimes 2. One is usually more common than the other, but there is the possibility of both happening, so we have to be able to differentiate them when we write their name. So here's what we do. To differentiate these two compounds, I'm just going to write them beside each other. Okay. I can't just go copper iodide and copper iodide, because obviously there's a problem there with two different things having the same name. So what we do instead is we put a Roman numeral inside of the name to tell us which number of electrons or which charge the metal has. In this compound here, since iodine always has a charge of -1, the copper must have a charge of +1, right? The compound's got to have an overall charge of 0. So in this case, this is the copper with a +1 charge. So I would simply write down here that this is copper 1 iodide. How did I know what iodine's charge was? Because it's not on your periodic table, is it? Right? All the metals have their charges written beside them, but the non-metals don't. They just have these blanks here. Right? So here's something you need to know. Everything in group 17, okay, that's above the staircase, everything in group 17 has a charge of -1. Right? The stuff moves to the left. The noble gases in group 18 have no charge. Then -1, then -2, and then -3. And then because for this we don't really write anything for these ones. Okay, so 18 has a charge of 0, 17 is all -1, 16 is all -2, 15 is all -3. Okay, for the non-metals. Don't go below the staircase, that rule doesn't apply then. Now, I see a bunch of you adding that to your periodic table. Just know that is something you need to know. If it's on your periodic table, you'll get a fresh periodic table for your unit exam. Okay, so it is something you need to know. 17 is 1, 16 is 2, 15 is 3. All right, this compound here, since this one was copper 1 iodide, over here, iodine still has a charge of -2, but how many iodides are there? 2. Right, so that means I have 2 negative charges in this compound in total. So how many positive charges do I need to get from the copper? 2. So this, since there's only one copper here, this is the copper with the 2+ charge. So I would write Roman numeral 2 beside it. You only use Roman numerals if the metal you're dealing with has more than one possible charge. So when you're looking at your periodic table, most of the ones through the middle are what we call multivalent metals. And they would have more than one possible charge. If you see that, then you will need to put a Roman numeral, the appropriate one obviously, in their name. Okay. Is the math of this overly challenging? Right. I just had to go, oh, this one has a -1 charge and there are 2 of them. 2 times -1 is -2. Okay, and then for this one here, I just have to figure out what plus -2 will equal 0. That much. Okay, everyone kind of follow me there? It's not mathematically challenging, it's just we have to get our head around the steps to do. So these are called the multivalent metals, and they run typically along the middle of the periodic table. Okay, so if I have a metal in an ionic compound that has more than one possible charge, I simply need to note that in its name. So this stuff here would be iron Roman numeral 2 oxide for this reason. Oxygen is in group 16, where everything has a charge of -2. Since a compound has to have a net charge of 0, this iron has to have a charge of +2. So I wrote the Roman numeral 2 beside it. Okay. What about this? Okay. Our usual ionic naming rules would say, call this iron oxide. But iron can be a 2+, as it is in this compound, or a 3+. So I've got to figure out which one is it here, right? Now, sometimes people just go, well, I'll just reverse the drop and swap. That'll tell me what the charge is. That's true about 2/3 of the time. Okay? I like to be right more than 2/3. I have a goal of being right more than 2/3 of the time. Okay? So here's what we do to figure out what the charge is on iron. Oxygen always has a charge of -2 because it's in group 16. How many oxygens are there here? 3. So how many negative charges do I have? Every oxygen's -2, and I have 3 oxygens. How many negative charges? 6. Okay, if every oxygen has a -2 charge, and there are 3 oxygens in this compound, that means that there are 6 negative charges in this compound. The compound can't have a charge in total, so how many positive charges do I also have to have? 6. Okay. I have to get those 6 positive charges out of how many irons? 2. What's 6 divided by 2? 3. This is the iron with the 3+ charge. Okay, it's kind of like using the drop and swap, but I can't just reverse it because that doesn't always work. Okay, as I said, it works about 2/3 of the time. And on a quiz or a test, you know I'm going to pick one of the ones that isn't of those 2/3. Okay, so that you're learning how to do this right. Okay, did I lose you? It's okay if I did. We're going to do lots of examples of this, so okay, it's okay to say, yeah, I'm a little lost there. Okay, let's try a different one. Let's try, okay, so when we run into one like this, let's start it out like it's any other ionic compound. What's Pb stand for? It's one of those weird Latin ones. It's lead, yeah. Okay, and O stands for? Oxygen. So this is lead oxide. But on my periodic table, I can see that lead can be a 2+ or a 4+. Okay, I need to figure out which one it is here. Incidentally, this is one of the ones where if you reverse the drop and swap, you'll get it wrong. Okay? So, in this compound, I have 2 oxygen atoms. And each oxygen atom has a charge of? -2. Okay, how many negative charges are in this compound? 4. Okay, so I've got 4 negative charges. If the compound's going to have an overall charge of 0, which all ionic compounds do, I need to get 4 positive charges out of the lead. And there's only how many leads? 1. So this lead has a charge of 4. And I put the Roman numeral 4 beside. Okay? So basically you multiply on the non-metal side and then you divide on the metal side. All right, in case you don't know the Roman numerals, okay? 1, 2, 3, 4, that's a V, 5, 6, 7, 8, 9, 10. This is why the Roman Empire fell. It had nothing to do with corruption and politics and war. Their numbering system was ridiculous. You won't probably even need to go beyond 7, okay, for what we're going to do, but those are the Roman numerals to 10. Most of the time you're going to be dealing with nothing above 4, okay? But there are 1 or 2 metals that have charges up to 7. Okay, can't have the same name, but contains the same stuff. We would start this out by writing it out like it was a normal ionic compound. Name of the metal, name of the non-metal ending in I. Then I look at my periodic table. Okay, do I need Roman numerals? Yes, I do, because it's a 2 or a 4. Okay, then I look to the non-metal. What's the charge on oxygen? -2. All right, there's only 1 oxygen here, so that means that the lead, since they're 1 to 1, must have the same charge. Agreed? Okay, so this is lead, Roman numeral 2, oxide. Okay, most common mistake I see with the Roman numerals is people either not doing it at all or doing it for everything. Okay, neither one of those is the right thing to do. You have to look at your periodic table and go, all right, if I have calcium chloride, am I going to need a Roman numeral? Nope, calcium only has 1 possible charge, so it doesn't need it. Okay, you only need the Roman numerals for the ones that have more than 1 charge. Okay? Questions on how that works? I would like you guys to try up to 4. We already did number 1. Okay? We already did number 1. It was iron 3 oxide. So you only got 2 to try here. Or 3 to try, sorry, 2. 3. So, for question number 2, follow the rules for ionic compounds. Same as always. CO. CO stands for cobalt, and S stands for sulfur. So this stuff is going to be cobalt something sulfide. Okay? Now, I have to figure out whether this is the 2 plus cobalt or the 3 plus cobalt, because it could be one or the other. What I do is I look to my non-metal. Non-metals only ever have 1 possible charge. Sulfur is always -2. How many sulfurs are there in this compound? Just 1. -2 times 1 is -2. Now, I have to get +2 then, so that this will equal 0, out of 1 cobalt. 2 divided by 1 is 2. So this is the cobalt with the 2 plus charge, and I put the Roman numeral 2 in here. Okay? Basically, I'm just doing the opposite for the metal as I did for the non-metal. Okay? For the non-metal, I went, okay, there's 1 sulfur here. 1 times -2 is -2. Then I transfer that number here to positive, and I go, that number divided by how many cobalts there are gives me the charge for cobalt. So on one side I multiply, the other side I divide, and I've got my number, and I just put in the appropriate Roman numeral. for number 3. Okay, oh, I don't know why I erased that. Chlorine is in group 17. Everything in group 17 is in -1. How many chlorines are there?
4.
Okay, so that means we have 4 negative charges. So I've got to get 4 positive charges from 1 manganese. 4 divided by 1 is 4. This is manganese 4 chloride. Okay. And for number 4, Cu is copper. And copper can be a 1+ or a 2+. It's with sulfur. Sulfur is always a -2. Okay, so what does the copper in this one have to be? +2. They're 1 to 1. That one's, you don't really have to do much on those. Okay, copper's got to be a +2. Okay, is that making a little more sense? It'll take some practice, but really it's just one little extra thing on top of the Ionic rules you already know.
Do you always have to have the Roman numerals and brackets?
Yes, the Roman numerals do need to be in brackets. Good question. All right, try the next 4 there. Let's have a look at these 4, guys. What does SN stand for? Tin, yeah. All right, so this is tin telluride, but tin has more than one possible charge, so we got to figure out which one it is. Tellurium is always a -2, right? Yeah. All right, so tellurium is always a -2, and there are how many? 2. So there are 4 negative charges in total. That means I need to get 4 positive charges out of the tin, the single tin that I have. So that means that this tin actually has a charge of 4. Yeah. So this is tin IV telluride. Okay. All right, number 6. What does Hg stand for? Mercury. And At is acetatide. Now, mercury can also have more than one possible charge. So we look to astatine. It always has a charge of -1, and there are 2 astatines. So we have 2 negative charges in total. That means we've got to get 2 positive charges out of 1 mercury. So this is the mercury with the 2+ charge. So mercury 2 acetatide. Number 7. What does PO stand for? Polonium. And it's with iodine, so polonium iodide, but it has more than one possible charge. Iodine is always a -1, and there are 4 iodines, so that's 4 negative charges in total. So I've got to get 4 positives from the metal. There's only 1 polonium atom here, so it has a charge of +4. Polonium IV iodide. All right, number 8. What's SB? Antimony, yeah. Antimony sulfide. Sulfur always has a charge of -2, and there are 3 of them. So we're going to have, 6 negative charges. So I've got to get 6 positive charges from 2 antimony. 6 divided by 2 is 3. So this is the antimony with the +3 charge. You can do all kinds of colors. Oh, we'll leave it with pink for a while. Okay, let's have you try the last 2 there. See how we do on those. All right, let's have a look at the last 2 here. So Ni stands for nickel. And it's with nitrogen, so nickel nitride. Nickel can be a 2+ or a 3+. Okay, it's with nitrogen. Nitrogen is in group 15, which has a -3 charge. And there are 2 nitrogens here for a total of 6 negative charges. Hey, guys. Please. So there's 6 positive charges. I've got to get those from 3 nickel. 6 divided by 3 is 2. So this is nickel, Roman numeral 2 nitride. And then for the last one here, Bi is bismuth. And I capitalized it, which I should have, bismuth. Okay, and it's with oxygen, oxide. Oxygen's in group 16, where everything has a -2 charge. -2 times 5 is? -10. Okay, so we've got to get +10 from 2 bismuth. 10 divided by 2 is 5. So V would be our Roman numeral there. Questions on that? All right. Now, let me ask you another question. What would you call this? Up until now, you've never had more than 2 elements in a compound, agreed? All right. So, this is still what we would consider a binary ionic compound. That means it only has 2 parts. The first part is lithium, the metal. The second part is this. This stays together. It's a single unit, but it is a charged particle, right? The charged particles are called ions. In this case, because it has more than one atom in it, a polyatomic ion. If you look in this chart at the top of your periodic table, you will see NO3 here. Okay? NO3 is called nitrate, and it has a -1 charge. So it's just like chlorine or bromine or iodine. It has a -1 charge. And we treat it just like we would anything that would also be a non-metal, right? So this is a polyatomic ion. So the name of this stuff would be lithium nitrate. So if you get a compound that starts with a metal, but then appears to have more than one thing after it, you're dealing with an ionic compound that contains a polyatomic ion. They're really easy to name because you don't have to change anything. All you have to do is look it up on that chart and write the name exactly as it appears in there. You don't have to change it. That's why that stuff is called lithium nitrate. We didn't change it to lithium nitride because that's something else. Okay, that would be lithium with just nitrogen. So all you have to do if you see a compound like this, so it's got more than 2 atoms in it, is find the other part of it in this chart and just write the name out. Right, so what would you call this stuff? Sodium. Sodium carbonate, yeah. Okay. And they work in every way, just like the other ionic compounds we've done. Even when we're writing the formulas, okay, you would still drop and swap. Sodium is a +1. Carbonate's charge, according to that, is? It's got a -2 beside it, right? Okay. So this is their charge right here. Okay. And on the periodic table, we can just look it up. But here, they tell us the charge beside it. So this stuff has a -2 charge. So when I dropped and swapped, the 2 went here and the 1 went here, but we don't write ones, so I didn't write it. Okay. It drops and swaps, they work exactly like the rules you've already been taught. Okay. It's just something you never had to do before. Okay. But writing their names is pretty easy. You just look up the name on there and write it out exactly as it appears. What about that one? This one's weird, isn't it? It doesn't start with a metal, does it? Right? And things that don't start with a metal are supposed to be molecular. But this one's not. Is NH4 up there on your chart of polyatomic ions?
Yeah.
Yeah.
What's its charge?
+4.
Positive 1. Okay, it just has a plus beside it, right? It's NH4. This 4 is part of the ion. The number up here, if it just says plus or it just says minus, that's 1. So -1 or +1. So that is a +1. It's the only one up there that's plus, which means it's the only one that acts like a metal. Metals all have positive charges. That's the only polyatomic ion that acts as a metal. Still doesn't change our rules. I write the name of the polyatomic ion, I write the name of the nonmetal, I change its ending to "ide," and I'm done. Okay? It doesn't really change anything except that you've just never had to use that chart before. Probably never seen that chart before. Okay, questions on how those work? There's one little trick with the drop and swap that we'll get to when we talk about writing formulas, but for right now we're just writing the names.
Do you have to do the thing where you take the 4 and turn into like a numerical or something? Or do you just leave it like that?
No, it's like any other metal, right? I don't put a prefix or anything in for that. I only need a Roman numeral if it's got more than one charge, and this is always a positive one. That's a good question. Okay. Any other questions on that? All right, I'm going to give you guys about a 3-minute break here, and then we'll talk a bit about molecular compounds. All right, let's quickly talk about our molecular compounds. Okay, so molecular compounds arise when 2 nonmetals react to form a new substance. So it's only going to be elements from the right-hand side of the staircase. Molecular compounds are only made of nonmetals. All right. In a molecular compound, unlike ionic compounds, the electrons are shared. Right? They're not traded. One doesn't get them and then the other. They're shared between the two. So if we're looking at a molecule like water, for example, it's 2 hydrogen atoms, that's these 2 green nuclei, okay? And then the nucleus here for the oxygen atom. If we're looking at the electrons, a hydrogen atom has 1 proton and 1 electron, right? And an oxygen atom has 8 protons and 8 electrons. Now, when we're looking at that outer ring, okay, this is a electron that comes from hydrogen. All right, so I'm just going to put an H beside it, and so is this one. Hydrogen needs another electron to fill its outer shell. Oxygen needs 2 electrons to fill its outer shell. So what happens is these 2 things go together and they share some of the electrons. Right? Now they're both happy, or all 3 of them are happy, because all 3 of them now have a full outer shell of electrons. Sort of. Okay? They don't get to keep that electron, they're sharing it. So they're utterly dependent on each other for their happiness. Okay? Unlike in an ionic compound where I got what I wanted, so now I don't need you anymore. Okay? Covalent bonds or molecular bonds are very, very strong because they have to stay together to have that outer shell of electrons full. Right? Does the difference make sense there? Right? All you really need to know is that in a molecular compound, the electrons are shared between 2 nonmetals. In an ionic compound, the electrons are traded from a metal to a nonmetal. That's the extent to which you need to know it for Science 10. Okay? Now, in terms of naming for a molecular compound, is that a molecular compound? Yeah. Sulfur is a nonmetal, oxygen is a nonmetal. All right. In these, do I use prefixes? I do. All right. And the reason for that is there's a whole bunch of ways that oxygen and sulfur can go together and share their electrons and be happy. Right? Unlike in an ionic compound, there's only one way for lithium and chlorine to go together, and that's it. Okay? In a molecular compound, because this could be S2O4 or SO2 or whatever. It could be a whole bunch of different compounds. Okay, they would all have the same name. So we have to use prefixes to say there's this many sulfur here and there's this many oxygen here. So this stuff would be, how many sulfur?
2.
2. What's the prefix for 2?
Di.
Di. So this would be disulfur. Okay, the first nonmetal gets its name written as it appears on the periodic table, so unchanged. The second one gets it changed to I. So this would be disulfur trioxide. The prefix for 3 is tri. Okay, disulfur trioxide. Second compound always gets its name changed to I. First compound always gets its name written as it appears. All right, that means we need to know the prefixes. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. You won't be asked to go above 10. Okay. Those prefixes I would allow you to have on your periodic table. If you wanted to write them on your periodic table, I would be okay with the prefixes being on your periodic table. Okay, so with those rules, what would we call this? Okay, how many nitrogens are there? 3. Prefix is? Okay, so tri-nitrogen. Tetrasulfide. There's 3 nitrogens, so tri-nitrogen, tetrasulfide, because there are 4 sulfides. Okay. Is that ringing a bell from last year? Okay, here's some good news. Nothing changes for molecular compounds. There's nothing I'm going to teach you that's new. Okay, you are going to do exactly the same thing you did in Science 9. There's no Roman numerals or other dirty tricks that could come in, okay, for molecular compounds. It's exactly the same as you learned last year. Okay, so when we're naming them, obviously the rules are you write the first atom, as it appears on the periodic table. Okay, the second one gets its name changed to "ide," and then you put in whatever appropriate prefixes are necessary for the numbers involved. Come on. All right, let's see what we remember from last year. Try the first 6 there. Let's see how we do. What's the only prefix that doesn't get used on the first element? Mono, okay? Chemists just have to have something to make themselves feel superior, okay? So they got to have some little trick in there, but you guys already know it, okay? Mono is the only prefix that never gets used on the first element. All right, let's have a quick look at these here, guys. So for number 1, do I need a prefix on nitrogen? No, because we don't use mono on the first one, so nitrogen. And what prefix would I put on the iodine? Triiodide. Okay, looking something like that. For number 2, what does C stand for? Carbon. Do I need a prefix? No. What prefix do I put on the iodine? Tetra. Carbon tetraiodide. Number 3, what prefix do I put on the nitrogen? Di. And on the oxygen? Tri. Number 4, what does TE stand for? Tellurium. Okay, no prefix on that because it's a 1. And diacetyl. Okay, and then for number 5, we would have diphosphorus. Yeah, diphosphorus. What prefix goes on the sulfur? Tri. Okay, and then for number 6, any prefix on the oxygen?
No.
Okay, what prefix goes on the sulfur? Right. So this would be oxygen, monosulfide. Okay, good work today, guys. Tomorrow, we're going to go over writing formulas for ionic and molecular compounds. Molecular is pretty easy because you just use the prefixes to tell you what number. Okay, but there are a few new things with the ionic compounds, especially with the polyatomic ions and the Roman numerals. Okay, so that will be tomorrow. That's what we're doing on Friday.